In manual metal arc welding, an electric arc is struck between a consumable electrode and the workpiece. In the tiny furnace of this arc, the electrode melts, forming a molten weld pool at the joint. Here is the simple principle. A flexible cable carries current from the power source to the electrode. An earth return cable is connected to the metal bench and workpiece to complete the circuit when the electrode touches the workpiece. When the electrode is brushed against the workpiece and then held a short distance away, an arc is struck and held steady. Then the electrode is drawn slowly along to produce an even run of the right thickness and penetration. For this type of welding, we need a large current at low voltage. And it must be adjustable. An AC welding set is just a transformer from which the output current can be varied either in steps by a switch or continually by a moving core. The transformer output can be rectified to DC, giving us the use of a wider range of electrodes. Or the DC can come direct from an electric, petrol, or diesel generator. All electrical connections must be sound. If not, they'll overheat and the arc will fluctuate. Permanent connections are secure and well insulated, so make sure that temporary ones are too, and always use a proper earth. The arc deserves great respect. Apart from the intensive visible light rays, invisible infrared and ultraviolet rays are also emitted. A brief direct look at the arc will cause severe irritation and watering with a prickling sensation like having sand in your eyes. This painful condition occurs some 4 to 12 hours later and is called arc eye. It'll pass in a day or so if bathed with an approved eye lotion, but it's much more sensible to avoid it in the first place by using a welding screen. The glass in the screen filters out the infrared and ultraviolet rays which do the damage. It also reduces the light intensity to a comfortable working level and protects your face and throat from severe artificial sunburn. A handheld screen is convenient for most jobs, but there's a head screen if you want both hands free. And with all those sparks flying around, it's not surprising that protective clothing is essential. Skull caps, aprons, sleeves, gloves, and spats are normally made in chrome leather. But asbestos is used when working with exceptionally high currents or where the job has to be preheated. If you wore them all, you'd find it almost impossible to work. Choose the ones most appropriate for each job. And with an insulating mat to stand on, you're safe to start welding. But first, let's have a look at that all-important electrode. Its design contributes a lot to the quality of the welds you'll make. Once, these electrodes were just bare wire, and they weren't satisfactory. The arc was unstable, large globules formed which caused short circuits, and air could get at the molten pool where it formed oxide skins which interfered with proper fusion. All in all, weld quality was often suspect. Modern electrodes have flux coatings with differing mixtures of mineral and alloy materials for different work metals and applications. These are the ingredients of a typical coating for mild steel. As well as dealing with the problems we've just seen, the flux may also contain metal powder to increase the amount of metal deposited. In slow motion, you can see it for yourself. The flux coating melts with the metal core, and gases are produced which keep the surrounding air from contaminating the weld pool. The coating also supplies a slag which helps to shape the weld bead, and the metal from the core is transferred in a stream of molten particles. The force with which the particles come off retains a wall of molten metal in the pool. All right, now it's time for you to have a practice run. First, fix the earth return clamp. Then, set the welding current, 170 amps for this exercise. Gloves next, very important. A clean flat sheet of mild steel goes on the metal bench. Having selected an electrode holder of the right amperage, insert a 4mm electrode for mild steel. Get yourself comfortable, allowing for free movement of the cable. Pick up the welding screen and make a dummy run to check that you can deposit a steady run of metal from left to right without stretching or awkwardness. Now switch on. Hold the electrode holder lightly at an angle of about 70 degrees to the travel and 12 millimeters from the plate surface. Protect your eyes with the welding screen and strike the arc by brushing the electrode across the surface of the plate. Draw the electrode along at a steady speed to deposit an even run of weld metal. The arc gap should be about 3 millimeters. Obviously, as the electrode melts, you'll have to lower it continuously to maintain this gap. If you don't, and the arc breaks, it will leave a crater. Like this. To fill the crater, restart by holding the electrode just below the highest point. This will restart the weld at the correct height, and you can continue with the run. At the end of the run, beware of a crater there too. Steer the electrode into a loop back over the deposited run until weld metal has filled the crater. Lift the electrode, breaking the arc and the current flow. But don't forget that the current is still on when you put the electrode down. Make certain that it's insulated from the metal bench and workpiece. Put on your chipping goggles to remove the slag with a chipping hammer. Clean up the work with a wire brush, and this is how it should look, a smooth, even run. It needs practice, of course. At first, you'll find it difficult to keep the arc length constant. You can feel the width of the gap by briefly touching the work surface with the electrode. If you leave it there too long, the arc will break and the electrode will stick, needing a sharp twist to free it. This is what happens when the gap is too long. The arc becomes erratic and large globules of metal cause too much spatter on the surface of the work. Make sure of the correct current for the job. If it's too low, metal will pile up in lumps of irregular width. If the current is too high, you'll get a flat deposit, a lot of spatter, electrode wastage, and difficulty in removing slag. Remember what it should look like before chipping away the slag and afterwards. Though, of course, it's not quite so easy to tell the difference when you're actually welding. Experience will enable you to manipulate the molten pool and to recognize the difference between weld metal and the darker colored slag. Your next stage is to practice runs at different speeds. A slower run naturally giving a thicker weld bead. Then, when you've mastered the straight run, you can make even wider runs, up to 4 times the thickness of the electrode core wire, by weaving the electrode from side to side in a slightly curved path. At each end of the movement, there's a short pause to ensure full fusion and to keep control over the larger pool. To increase the thickness of a component, you can make any number of overlapping runs. These are made with the electrode at about 70 degrees to the direction of travel and pointing into the previous run at about 60 degrees. Runs should overlap by about 1/3 of their width. This is called reinforcing, or if the metal is especially wear resistant, it's called hard facing. The runs must be built up level with each other, no ridges or valleys, and slag must not be trapped between runs. When you can do this, you'll be ready for Metal Arc Welding Part 2, which deals with real joints between two components.